All right, so I want to summarize the chapter first. So all the topics that are going to be on the quiz. All right, the entire chapter. I'll just give you the whole chapter, and then give you the whole chapter, and then we'll work through some problems that we'll see. So, big ideas. We have work and energy. The work done on an object, if I have an object, have a force that's applied over some displacement, with the displacement in that direction, that work is equal to FD cosine theta. Remember, if F and D are in the same direction, that works out to be a positive work. If F and D are in opposite direction, that works out to be negative work. And if F and D are perpendicular, that gives a zero work. All right? And then in energy, we have two different types of energy. We have the kinetic energy, is 1/2 mv squared. That's the energy of motion. And then potential energy is an energy of position. That's mgh. Remember, this is the speed, not the velocity. So there's no sign attached to it. It's a scalar quantity. Both of those are scalar quantities. They're both measured in joules, or the equivalent, which is a Newton meter, right? Remember, work and energy are equivalent to one another. So that's the first big idea, or several ideas contained. The next is the conservation of energy. And that just says that the energy at one point is equal to the energy at another point, or the initial is equal to the final energy. And then in particular, we're looking at mechanical energies, so that would be kinetic energy plus potential energy at one position is equal to the kinetic energy plus the potential energy at another position. And the problem that you'll have will be like one of these problems where you have some object that will probably start out with some speed. It could start out with a zero velocity, and then you have to figure out what is the speed and or position at other points in that. We'll work through a problem like that. That's conservation of energy. Also, the free fall problem, or the problem where you have something that goes up and then comes back down again, which is really the same problem, just worked out a little bit differently, or rather in a slightly different context, but the same problem. We'll work through one of those. So conservation of energy. And then the next is the work energy theorem. The work energy theorem says if I do work on an object, I change its energy. Sometimes that work will cause a change in the potential energy, and sometimes that work will cause a change in the kinetic energy, and it'll depend upon the context. So say, for example, if I have an object and I apply a force over a certain displacement, then that causes a change in potential energy because I move it up to a different value for h. And by the way, that works on an inclined plane too. If I have this force acting over a certain distance, then that causes a change in h, or a change in potential energy. We'll look at a problem like that. And that's like your lab, actually, that y'all did last week. And then also work will cause a change in kinetic energy if I apply a force over a certain distance. So apply a force, apply a force over a distance, that's going to cause the object to accelerate, which will give it additional kinetic energy. Notice that this example with the kinetic energy, the object's not changing height, and on this position, on this one, the object will always have acceleration equal to 0. So you'll always be dealing with a constant velocity for this scenario, and constant velocity here, that means the kinetic energy isn't increasing, and over here you'll always be dealing with a constant height, so it'll always be at the same vertical level. Unchanging kinetic energy on the left, unchanging potential energy on the right. So all that work is either going into potential or kinetic energy. Also, don't forget about the work done by friction. This is still under the same heading. That is equal, well, same, F times D. But notice that since F and D are opposed to one another, that this is always going to be a negative value. All right, and then the final thing, which is not on our quiz for tomorrow, Wednesday, not on our quiz, is elastic potential energy. Let's just go ahead and, I'll just go ahead and include it here so you get a full picture of the entire chapter as you're preparing for the exam coming up. The elastic potential energy, there are a couple of things here. The first is that the force is equal to negative kx. This is called Hooke's law. It just says that if I have a spring and I compress that spring, say I compress it down to that height, that I get a force that the spring exerts. And that force is equal to the spring constant times the compression of the spring. So this is called the spring constant. Sometimes it's called Hooke's constant. And this is the compression of the spring. I left the negative off. Don't worry about the negative right now. We'll talk about that in class. The more you compress a spring, the bigger force is required. And then the other thing that has to do with elastic potential energy is that if I compress a spring, there's my spring, if I compress it by a certain amount, x, then the elastic potential energy, I'm going to call it PE of the spring, is equal to 1/2 kx squared. That is the energy contained in the spring. And so we'll begin tomorrow and Wednesday and Friday. We'll begin doing these types of problems, but with springs in them. So here, instead of having gravitational potential energy, we'll have elastic potential energy. You'll see they work out the same way. It's just you're using a different type of energy. But don't worry about that for the quiz. Don't sweat that now. And then the other thing that's not on the quiz, I think we've already seen it though, is power. Power is work over time, or sometimes we might talk about it as energy over time. It is in units of watts. I don't think we've done this yet, have we? We talked about power yet? Yeah. Anyway, not on the quiz. So these two things are not on the quiz. Power, on the exam, you're probably just going to have one question, but nothing on the quiz. Nothing about elastic potential energy, but all of this other stuff, all this other stuff is on the quiz. Okay? Make sure you know your units, how to find your units. Make sure you know how to do this work energy theorem. There are a couple problems about that. Make sure you do the conservation of energy. There are a couple of problems and conceptual questions about that. And then just calculating the work, calculating the energy, or, understanding the relationships between these variables like we did in class today. How they're related to those variables. Now, if you've been sort of tracking along as we've been going through the class, you'll know how to do that. It's just you have to know the formulae and then look at them. But it comes with practice, of course. As I told you in class, every question is from the past exams. I don't change them. Even if you just memorize the answers to all those questions, I'm okay with that. That will help you for the upcoming exam. Exam 3, there is one exception. Let me show you on fall 15. Oh, I don't have it here. Let me pull it up on the website. Fall 15, there are a few questions that I had in exam 2. I think it's fall 15. A few questions from exam 2. Yeah, here we go. So it looks like the last, from 22 down, this is fall 15 exam 2. From number 22 down through the end is all okay. Fall 15, number 22 to the end is potentially a problem. But they're really similar problems on the other exams. So if you don't practice that, that's fine. But no, just go ahead and practice it. Practice them all. 22 to the end on fall 15. But otherwise, yes, all exam 3. Up to usually about 10 or 12. Number 10 or 12. Okay? All right. Are there particular questions that y'all want to look at? No, Elena?
So there's 2 questions that are kind of similar with the work energy theorem, but I'm just curious as to how they're worked out differently.
Okay, let's see.
Fall 2020, number 4, is the first one, and then the other one I think is 5/1/2018.
Okay. So, what was the other one? 5 on 18?
2018.
Okay, let's look at that one first. I worked this one in the last help session. I'll come back to it. But let's look at that other. I just want to look at this one so I'll know. Okay. And then 2018, you say? Y'all printed out these? Oh, these are in your workbook, aren't they? Okay, yeah, these are slightly different problems. Let's work this one first, and then we'll go back. I think that the other one's really similar to this. It's just the final condition is a little bit different. So I have a cardboard box sliding upon a horizontal frictionless surface, and it's traveling at 6 meters per second when it encounters friction. So it's traveling along at 6 meters per second, everything's going okay, it's going to keep going on forever and ever and ever unless it encounters a force, and then all of a sudden it encounters a force. And then it starts to slow down. So here's my box right here. It's traveling at 6 meters per second. After a distance of 2 meters, it is now traveling at 4 meters per second. And I know the mass, right? No, I don't. I don't know the mass. So what's happening here is I have a change in kinetic energy, because it's going from big kinetic energy to smaller kinetic energy, from 6 to 4 meters per second. And then that is equal to the amount of work that's being done. This is the work energy theorem. You're right, you said that. The change in kinetic energy is the amount of work that's being done. The kinetic energy is 1/2 m times 6 squared minus 1/2 m times 4 squared. Oh, look, I'm going to rewrite that just a little bit. It makes the math a little bit easier. 1/2 m times 6 squared minus 4 squared. You'll see what I did there? Pulled out the 1/2 m because it was a common factor. And that's equal to the work that's being done by friction, which is the frictional force. I don't know that right off, but I can figure it out, or we'll work on that, times the distance. And this is what I'm looking for. Now I have a couple problems here because I don't know the mass and I don't know the frictional force, but I know that the frictional force is equal to mu times the normal force. Oh, but this is a horizontal surface, so the normal force is equal to what? Is equal to the weight. When I'm on a horizontal surface, the normal force is equal to the weight. So it's going to be equal to mu mg times d. Look, this whole thing right here is the frictional force, mu times the normal force. And this is still 1/2 m. That's 36 minus 16, so that's 20. I don't square it, right? I squared it on the inside. And then notice here my masses cancel out, so those cancel. This is a little bit more difficult problem than that other problem, isn't it? Yeah. So this is equal to 10 equals mu is given. That is, oh no, I'm looking for mu. 0.2, excuse me, not 0.2. I'm looking for mu. Mu times 10 times the distance, which is 2. So mu is 10 divided by 20, or 0.5. Now let's step back through that, what we did. That's the right answer?
Yes.
Okay. So, work energy theorem. If I have a problem that's slowing down, the object is slowing down and friction, that's work energy problem. You're always going to start with W equals delta E. I figure out what is my change in kinetic energy. I'm a little thrown off at the first because I don't know the mass, but just hang on tight. It's probably going to cancel out at the end. Sometimes I just don't give you the mass because it doesn't cancel. Sometimes I give you the mass and it does cancel. It's probably easier just to not write in the mass because you're just dealing with fewer numbers. And then I don't know the frictional force, but again, I'm staying calm. Everybody calm? Yes. Okay. A little bit nervous. I stay calm because I know what I can replace that frictional force with, my mu times my normal force. I know my distance, and so then I'm solving for this mu. Let's go back and look at that other problem. What are there questions about this one? Haley?
How did you know you were doing kinetic?
As opposed to potential energy?
Just like, how did you know, like, I guess where to...
I think, well, I don't think, because I'm talking about velocities here, I have a change in velocity that I have, that should key me in that I'm talking about kinetic energy. If I was instead talking about a change in position, in vertical position, then that would be a clue to me that I was talking about potential energy. Okay? Let me just make sure that this is clear in case y'all do it this way. This 6 squared minus 4 squared. Just want you to recognize that 6 squared minus 4 squared is not equal to 6 minus 4 squared. Those are not the same, right? This one is 36 minus, this is 20, this one's 4. Not equal to one another. So be careful of that. When you're taking a difference in the kinetic energies, that you have to square the velocities first and then take the difference, if you do it this way, which is probably a good idea. Can we go back to that other one? Oh, Faith, go ahead.
So why are we squaring 6
Oh, because this is our change in kinetic energy, which is 1/2 mv squared minus 1/2 mv squared. This is final, initial. This one is the final velocity. This one is the initial velocity. The reason they're squared is because it's wrapped up in that kinetic energy. Huh? What? Oh yeah, you're right. It is that is the initial, but no, it doesn't really matter. I'm just looking for the difference in the energy. Okay? Haley? Okay, I want to know the difference in the energy here and here. And whatever that difference in energy is, that's the amount of work that is being done. Now, Jonas was pointing out correctly that I flipped my final and initial, but it doesn't really matter because I just want to know the difference in the energy and I'm going to set it equal to the work. In fact, I don't even really worry about the signs because I know that difference in energy, that's the amount of work that my frictional force is taken away. Did that answer your question? Yeah, that's a good question.
Okay.
Okay. Tough question. Like one of the tougher questions on the old exam. Let's go back and look at this one. In fact, I'm just going to erase it because it's worth redoing. This one, both are worth looking at. So you might have already worked this one. If you did the previous help session, you did. But let's just look at it again afresh. Hopefully everything I say here will just be easy for you. So here, it's a very similar scenario, and you're going to have, I'm pretty sure, a similar question. I like these kinds of questions. Where I have an object, I give you its speed and its mass, and I give you the coefficient of kinetic friction, and I just want to know how far will it slide. I think this is an easier question, but it uses some of the same ideas. I have some kinetic energy. I want to know my final kinetic energy is 0. So all the energy that this object has, I'm going to take away. And the way that I'm going to take it away is by applying a force over a distance. So my kinetic energy is equal to the work done by the frictional force. That's 1/2 mv squared is equal to the frictional force. That's mu mg times the distance. That's what I did before. This is my kinetic energy. This is my normal, this is mu. This is my normal force because it's on a horizontal surface with no other forces at work. That's important, right? That there are no other forces pushing down or pulling up on it, times the distance. So here, I can cancel my masses. They go away because they're on both sides and in both terms. And I'm looking for, what am I looking for? I'm looking for D. So I'll go and put in some numbers here. 1/2 of V, which is 2 meters per second squared, divided by mu, which was 0.2, times G, which is 10. That's equal to D. That's 2 divided by 0.2, that's 10. That's 1, right? Isn't that the answer? 1 meter. Okay?
Just clarify. So the reason you don't subtract the kinetic energy is because it comes to rest in this one in comparison to
That's
the
right.
others?
I did subtract them, but I said 1/2 mv squared minus 0.
Okay.
Oh, really, I did, right, Jonas? 0 minus 1/2 mv squared. If you really want to be technical about it, because 0 was the final. Doesn't really matter if you get those flipped. I'm just looking for the difference in the energy. Okay? Good questions, y'all. Other Haley? In a problem like this? Well, let's sort of, we had those 3 big ideas: work energy theorem, conservation of energy. Let's sort of look through this exam, and we'll look at those particular instances of when I'll know, do I use this or what? Let's look at a fresh exam that I haven't written on. Let's look at this one. So number 1, in this problem, it looks like it might be a work energy problem, but I'm looking for how much work does friction do on the kid. There's no mention of what's his speed or what's his change in speed. In fact, it doesn't say anything about that. So in this problem, I know that it's a simple work problem. Work is equal to force times distance. I'm looking for the work that's done by friction, because there's no mention of speed. Yeah, really just that. There's no mention of speed. That even though there is a change in kinetic energy for this kid, that I don't talk about that anyway. So I'm really just looking for the work. So in this case, the work is the frictional force times the distance, right, which is the frictional force of 10 newtons times the distance that he travels. This is tricky. Is it 3 or 5? 5, right. We did this problem today in class, I think. So that's equal to, and then, no, that's it, 50, right? Now, if you have a problem like this one, it's going to key me off that it's work energy theorem because it has that velocity. In fact, is that always true? Yeah. If you have a velocity, it's either conservation of energy type problem or a work energy problem. For conservation? Oh yeah, this is 2019. We've done most of these. Number 5 is talking about change in height and change in velocity. So it's talking about height and it's talking about velocity or speed. So I know then that this is a conservation of energy problem. All right, and that's why we're doing this. Kinetic energy plus potential energy equals kinetic energy plus potential energy. Okay?
So is it basically when there's height and velocity conservation, and when there's horizontal and velocity coordination?
That's always true. Yes. Okay? If there's a height and a velocity change, that's conservation of energy. Is that always true? I think that's always true. Yeah, I'm thinking there was a problem. I don't know where it was. I think we've done it where I have a kid that comes down, or some object that comes down a slide, we'll say it's a 3, 4, 5 triangle, and he has some frictional force acting on him. And let's say his mass is 2 kilograms and mu is 0.1. And what is the velocity when he gets to the bottom? Oh, so this is a hybrid problem. Let's work this one. So I don't know which one this is, but there is this one similar to this in the exams, where I want to know, if I have this kid coming down the slide, what's his velocity when he gets to the bottom? So this is an example that is counter to what I just said to you, Faith, where I have a change in potential energy and a change in kinetic energy and a work that's being done by friction. Yeah. Mm-hmm.
But in any other terms, it would be height and velocity.
Yeah. Yeah. But you know, y'all are coming up with these rules, and that's fine. But rules you're gonna forget. If you just sort of stick to those basic principles about what is work and what is energy, that's always going to serve you better than a bunch of rules. Because if you come up with a bunch of rules, even if you do really well memorizing them, you're going to get them mixed up. You're going to get them. It's just not going to work out very well. Okay. Let's look at this problem. So I have this thing coming down a slide, and I want to know the velocity at the bottom. Now, if there was no friction, I would just say mgh, that's the potential energy at the top, is equal to 1/2 mv squared. My masses would cancel. This is 10 times 3 equals 1/2 v squared. So v is the square root of 60, which is approximately 8. We did a similar problem to this today. Now, did I make y'all do that? Yeah, I divide both sides by 1/2. Or multiply both sides by 2. Yeah. I don't know if I do that to you. So let's just say the normal force. Well, what is the normal force? This is 37 degrees, right? It's a 3, 4, 5 triangle. So the normal force is 20 sine 53. Don't mind me. That's 16. I think in this problem I actually told you what was the frictional force. No, let's just do it that way. Never mind. Forget about the normal force. I try not to bring inclined planes into this where you have to figure out the components of the forces. Okay, so let's say that the frictional force was equal to 2 newtons. Okay, and then what is the speed at the bottom? I know it's going to be less than 8 meters per second, because now I have this frictional force slowing the object down. And so it's going to be the potential energy minus the work done by friction will equal to the kinetic energy at the bottom. It's potential energy at the top, kinetic energy at the bottom. So that's going to be mgh, where h is 3. Haley? Okay, yeah, so I'm sort of doing a hybrid of the work energy and the conservation of energy. I have the energy at the top on one side and the energy on the bottom at the other, but in order to get there, I have to include this term. This is the total amount of energy it has at the top. This is the amount of energy that the friction takes away from it as it moves down the slide. And this is the energy that's then left over. The potential energy at the top, that's mgh, that's the total amount of energy that it has. As it moves down the inclined plane, that frictional force takes away energy from that block. So when it gets to the bottom, it now has less energy than it did when it was at the top. And this formula is not on your equation sheet, right? This is something that's we hobbled together from these two different ideas coming together. All right? I know you don't like that, do you? You don't like that. It's okay, you don't have to like it. Minus the frictional force, which is, we said it was 2 newtons, times the distance, which is 5 meters. So that's the energy, 10 joules that's been taken away, equals to 1/2 times mv squared. So my mass was 2 kilograms, that's 2 times 10 times 3, that's 60, minus 10 equals v squared. So v is equal to the square root of 50. I did 1/2 of 2 here, by the way. That's 1 v squared, which is equal to 7. I think we did this exact problem in class today, actually. But it's a good problem. It's one of the more difficult, conceptually and mathematically, problems. And you're going to have, and you are going to have a work energy theorem. I'm pretty sure you have an inclined plane type problem, which would be something like this. I'm pretty sure it's on the quiz. If it's not on the quiz, it'll definitely be on the exam. So, Jonas? Okay. Well, potential energy, you're looking for a change in height. Kinetic energy, you're looking for a change in speed. And then work, you'll have some force acting over some distance. I know you're looking for rules, and I think that as you work through the practice problems, those rules, you'll begin to see that really the only rules that we have are that first page where I laid out the basic principles. That's always the best way. Okay? Other particular questions? Jonas?
So you said potential energy minus the work done with friction equals the kinetic energy in that problem.
Mm-hmm.
So how do you know? How do you know whether to add something or subtract something from in your latest one?
Not making sense to me, man.
It's hard.
I don't know to subtract the frictional work. Okay. Yeah, so again, it's this idea that my frictional force takes away energy. I start with this amount of energy, I take away this amount of energy, and I'm left with this amount of energy at the bottom. Start with some, I take some away, and then I'm left with that. And that's how I knew then to put this minus sign right here, because I'm taking away that frictional force. That frictional work, rather. The work done by the frictional force. Okay? Elena?
Number 6 on fall 14.
Just want to, I try to keep my questions more recent, but sometimes I will dip back into those 13, 12, 11 exams. But really, they're all very, very similar. So if you can work through 2014 to 2020, it'll be fine. But if you're really just trying to memorize them, you want to go back farther. Don't try to memorize them. There's too many to memorize, right? Too many to memorize? Which one? 14? What number?
6.
Yeah, so this is a good application of the conservation of energy. I have a block at 5 meters. It drops to 2 meters from the ground, and I want to know what is the total energy at this point. Now I know that total energy is the sum of the kinetic energy plus the potential energy. Right? It has both. It has both kinetic and potential energy. But it's also equal to the energy up here, which it only has potential energy up here. So if I can figure out the energy at the top, that's going to equal the energy at 2 meters. So the whole 2 meters thing, it's just like a, what's that word? Distractor or something. That's not really important. because if I know the energy at the top, then that will answer my question. So that's going to be mgh, that's 40 kilograms, times 10 meters per second squared, times 5 meters, it's 400 times 5 is 2,000 joules. Okay? The energy shifts from one type of energy to another. So here at the top, it only has potential energy. As it moves down, it gets less and less potential energy, but more and more kinetic energy. But the sum of these will all, like the sum of this will still equal 2,000. That's the conservation of energy, that the total amount of energy remains the same. Okay? So here, I know there's only potential because at the top, the speed is equal to 0. It's resting at a height of 5 meters. So the speed is equal to 0. That means no kinetic energy. Here, at 2 meters, I know that it has kinetic energy because by that point, it has some speed. It's fallen for over 3 meters. But it also has some height. So if v is equal to 0, that means the kinetic energy equals 0. If height equals 0, that means potential equals 0. Potential energy, excuse me. It's something different from potential. Potential energy. We'll get into that next year, next semester. Potential energy doesn't go away. We'll have a whole chapter on it next semester. That'll be the second hardest exam of the whole year, I think. But by then, y'all are all going to be champs at vectors. It's all just going to be like review by then, right? Review.
Atom, like electrons, will have potential energy, and then as it goes down, as it goes closer to the nucleus, it becomes elusive energy, and as it goes further from the nucleus, it has more energy. Is that kind of what
It has more energy as it gets closer to the nucleus.
Yes.
Yeah. Mm-hmm. Yeah, because the force, the electric force acting on it increases.
So there's electric force versus this, I guess, more natural force differ?
No, they're a lot the same. We're going to talk about this next semester, actually, in that chapter 2, which is the hardest exam, the second hardest exam of the year. So we'll talk about that, like where that comes from. And you chemistry majors, y'all will do that in BChem. It's exciting. No, it's good class. Dr. Lowe is the best physical... No thumbs down for Dr. Lowe. Yeah, he's great. He's the best physical chemistry professor in Louisiana, the United States, the world. I don't know. He's really good. It's a tough course, but he makes it easier for the students. So, okay. Let's look at some of these conceptual questions. We're in fall 14, so let's just sort of review some of these ideas. I know that hopefully you're good at the math problems, but you know, half the quiz is going to be conceptual problems, so don't neglect those. Which of these is a conservative force? Not air resistance. You lose energy with that. That's a dissipative force like friction. Convection, that is a thing, but it's not related to a force. Gravity or friction, then? Which of those is conservative? Gravity is conservative. Field forces are conservative. Contact forces are not conservative. Conservative means you conserve what? Energy. Conservative in physics always refers to energy. No springs. When you increase in speed, oh no, never mind. That's chapter 6. Do y'all have this 2014 exam in your workbook? Y'all just, you have it like, you print it or you have it on your iPad or whatever. How about this one? Which force is doing 0 work? That would be A is doing zero work because the force and the displacement are perpendicular. Two trailers have different masses, 500 to 2,000 kilograms, and they have the same speed. What is the ratio of the kinetic energy of Y to X? Well, Y has the bigger energy, X has the smaller energy, so the ratio is going to be what? 4 to 1, right, because this mass is 4 times this mass. See that? That's a good standardized test question. MCAT, GRE, that sort of thing. They like to do ratios on those exams. Which of these is true? Oh no, that's chapter 6. I have a lot of mix of chapter 6. Anytime you see momentum, you can disregard that question. That's chapter 6. Let's go back up to a more recent exam. Was that a question or just a stretch? Okay. You're going to have a conservation of energy problem. I don't remember if I asked you what are the types of energy that they have on this exam, but certainly on the exam, I'll ask you that. I don't know if it's on the quiz. This asks, at point C, this is fall 16, by the way, at point C, describe the potential and kinetic energy. I know it has potential energy, so potential energy is bigger than 0. Does it have kinetic energy? Yeah, since it had kinetic energy here, if it's at a lower position than there, it will also have kinetic energy. So it has kinetic energy too there, right? I mean, y'all been on a roller coaster, right? You start up really high, and then you go down, then you never go as high, you just stay lower until you get the chain, and then it brings you up to another high height, and then you do it all over again. You been on a roller coaster? Yeah, my wife loves roller coasters. All right, so PE and KE are both greater than 0. Conservative forces require contact. Field forces conserve energy. Ding, ding, ding. Yes. Friction is a conservative force. Conservative forces are path independent. I think we answered that question in class today. If y'all have particular questions, stop me. Jonas?
It's just for the conservation. Yeah, conservation of energy. You have point A and point B.
Mm-hmm.
Yeah, the energies of point A, the energies of point B, right? Potential.
Right. Yeah. The sum of kinetic and potential is equal.
Yeah. So when you set those equals equal, and you see that point A doesn't have kinetic, you just kind of take out kinetic and just set potential energy of A equal to kinetic.
Mm-hmm. Can we work this problem? I think you're asking about number 2.
I'm not. It's just somewhat. I just thought.
Ask.
It's just a question I had.
Ask your question again. I'm not sure if I answered it.
Okay, so with the conservation of energy, it's the energies of E1, E2.
Mm-hmm.
So let's say, sure, this one goes. So, energies of A equals the energies of C, let's say, and A didn't have potential energy. Could you remove that from the equation?
Right.
And just have kinetic energy of A is equal to kinetic potential energy of C.
That's correct.
That's how.
Yeah, let's work. I don't think we've worked one like this, and you'll see how that works out here. Because in this one, we're looking at A and E, and I'm told that at point E that it comes to rest. And since it comes to rest, that tells you that I have potential energy, but my kinetic energy is 0. I have no kinetic energy there. Over here, I have a height, so I have potential energy, and I have a speed, so I have kinetic energy. So it's PEA plus KEA is equal to PEE, which I guess is like P. I'm sorry. That was very middle school, wasn't it? My daughter is in middle school. It's her last year of middle school, but that's a middle school boy joke, right? Not a middle school girl joke. She's like already 16 almost, it feels like. Anyway, So this is mg. I like to just go ahead and write in the heights here because I don't have to use the subscripts then. mg times 10. That's this 10 right here, not the g10. Plus 1/2 m times 4 squared is equal to mg times h. Even if I'm given the mass, I don't write it in because I know on these questions my mass is just going to cancel out. So that's 50 plus 8 equals 10 times h, which is what I'm looking for. So h is equal to 58 divided by 10, or 5.8 meters. What? Did I do something wrong? Oh no, this is not 50. Yeah, this is 100 plus 8. That's 100. That's 10.8 meters, or 11 meters. You're certainly going to have a conservation of energy problem on your quiz and on your exam number 3. It'll be part of the free response. Okay? Other particular questions? That was a whirlwind. Y'all like Monday at 2? Does that work well for y'all? Is it better than Friday at 2? It doesn't matter? Okay.